In section 4.7, we're going to talk about modeling with higher order polynomials. So essentially creating algebraic equations with degrees 3 or 4 usually that will model real world situations. All right, so in this first one we have sort of a description. The top and bottom of a cardboard box are squares with sides of length x inches, and the height of the box is 18 minus 2x inches. The first thing we'd like to do is to write a function v of x that represents the volume of the box. So I know that in general, the volume of a box is length times width times height. And in this case, if I think about my little box here, it says the top and bottom are squares with sides of length x. So that's an x by x square. And the height is 18 minus 2x. So if I multiply that length, width, and height together, I'll get x times x, or x squared, times 18 minus 2x. And I'm just going to finish multiplying that out. 18x squared minus 2x cubed. And so now I've got volume expressed as a function of x. All right, it says, although the function's a polynomial, so technically the domain of any polynomial is all real numbers, there's an effective domain that allows this to be realistic. First of all, certainly x has to be greater than 0, right? You can't have a negative side of a box. But the height also has to be greater than 0. So 18 minus 2x needs to be bigger than 0. Let's see, if I subtract 18, negative 2x is greater than negative 18. I'll divide both sides by negative 2. And since I did divide by a negative number, I have to reverse my inequality. So I get x is less than 9. So all of the x values have to be bigger than 0 but less than 9, meaning my domain goes between 0 and 9. And I can write it in interval notation like that. All right, in part C, we'd like to find the volume of the box if the square top has sides of length 7 inches. And it asks us to think about it two ways. So I'm going to first of all say, well, I have my function v of x here. And what they've essentially told me is that since the square is 7 inches on a side, x is 7. So I could just plug my 7 into the volume equation. And I can find my volume that way. Let's see, 18 times 49 minus 2 times 7 to the third power is 196. And this is all in inches, so the volume would be in cubic inches. A second option for finding the volume would be to go back to the idea that volume is length times width times height. And again, just a reminder, the box looks like this. And since they've told us that the length is 7, the base is 7 by 7, and I could plug 7 into here. 18 minus 2 times 7. So 18 minus 14 would give us a height of 4. And we could just calculate the volume that way as 7 times 7 times 4. And when we do that, 49 times 4 is also 196. All right, continuing, with this problem, they ask what dimensions of the box give us a volume of 160. And we're supposed to do this problem twice, once with the techniques from this chapter, by hand, and then also graphically. So if my volume is 196, I'm going to take that volume equation that we already found, and I'll set it equal to 196. If I'm going to solve this really either by hand or by graphing, I would want to make sure I get this equal to 0 first. So I like a positive leading coefficient. I'm going to move everything to the right. So that would make that a positive 2x cubed, a negative 18x squared, and then the plus 196 is already there. I can factor out a 2. Might as well do that, make my numbers just a little bit smaller. Is that 98? And I now have a trinomial that I might want to try to factor. Unfortunately, notice this is not quadratic form, right? You have x squared, and then not x to the 4th, which we would need for quadratic form, but rather x cubed. So I'm not going to be able to factor this, and instead I would have to do this using the rational zeros theorem. So for my p over q's, I know the p has to be a factor of 98. So I could go with 1 and 98, 2 and 49, and I think I'll leave it to you to check this, but 3, 4, 5, 6, none of those go in there. The last thing that goes in evenly is 7. And 98 divided by 7 is 14. Okay. And again, if you want to check that a little bit with a calculator, you can pause and do that. But those are the only factors of 98. The leading coefficient is really 1 here. So that's going to make things just a little bit easier. The denominator has to be factors of 1. And of course, the only factor of 1 is 1. So I have 1, 2, 3, 4, 5, 6, and then all the negatives would make 12 possibilities to check here. Let's pop over to Desmos, and I'm going to get the graph out of the way for now because we are going to solve this graphically later. But this time, oops, I got to put a function in first. This time I'd like to solve it algebraically. So I'm going to put in my function as, I could put the 2 in there, but I don't really need to. I'll go ahead. 2 times x cubed minus 9x squared plus 98. Just putting in the factored form. And then I'm going to check my possible rational zeros by asking Desmos to plug them into my function. All right, looking for 0. There's one of them, x equals 7. All right, and that's it. So x equals 7 is the only rational 0 that we found. And so I'm going to divide that out of my function here to see if I can help get myself a factored form that will help me out. So 7 there are 0 x's there. Put that 0 in, and then the 98, the constant term. Right? Again, there's no x to the firsts. That's why I put that 0 in there. And then just a quick little synthetic division here. And there we go. Remainder 0 as expected, since I already knew that was a 0. And I can therefore say that I could rewrite this in factored form as 2 times x minus 7 times x squared minus 2x minus 14. Squeeze that in there. There we go. All right, so we know that 2 can equal 0. Either x minus 7 equals 0, or x squared minus 2x minus 14 equals 0. First one gives me x equals 7, which we already knew, right? That was the one we found with the rational zeros theorem. But I'll get a couple of other options over here from my quadratic. Now, I don't believe that's factorable, so I'm going to go ahead with a quadratic formula. That would be 2 plus or minus the square root of negative 2 squared minus 4 times 1, sorry, I'm running out of space here, times negative 14 over 2. Should have left myself a little more room. So that would be 2 plus or minus the square root of, let's see, I'm just going to put that into my calculator. That is 60 underneath that square root. And I certainly could simplify this if I wanted to, but in a real world problem like this, we're probably going to want to give the answer as approximate decimals anyway. Not real meaningful to say the box is, 3 plus the square root of 5 units long. So I think this time, instead of simplifying that, I'm just going to go ahead and put that into my calculator. So I would have 2 plus the square root of 60 divided by 2. So about 4.37. Oh, I'm so sorry. I typed that in there wrong. Let's fix that. That should be 2 plus the square root of 60, not 1. There we go, 4.87. At least it was easy to fix. All right, and then the other one is 2 minus the square root of 60 divided by 2. And that one's negative 2.87, which I don't especially care about, right? I can't have a negative length. So this one's not part of the effective domain. It's not part of the domain of the realistic function. So I get 2 possible answers here that actually may work for my box. We'll talk about the full dimensions in just a minute, but let's just double check this graphically first. Desmo's back here. If I bring this graph back over, turn off these points, and that's going to be that negative 2.87 that we already said isn't realistic. There's the 4.87, and there's the 7. So we're seeing the same answers as what we got using the algebra by looking at the graph. All right. I now want to go back to the original question, which I haven't quite answered yet. The question asked me to find the dimensions of the box. So far I've solved for x, which is a really good start. But remember, again, this box looks like this. The base was x by x, and the height was 18 minus 2x. So I've got 2 possible boxes. In box 1, I'm going to use this x equals 7 that we found, right? One of my solutions. If x is 7, this box would be 7 by 7, And then 18 minus 2 times 7, 18 minus 14 was 4. So that's one option. The second possible box has the x value of about 4.87. So again, the base is x by x. So 4.87 inches by 4.87 inches. And then I'd have to do 18 minus 2x to calculate the height.